It was the kind of day most people don't remember. A day too ordinary, too quiet, too settled in its own rhythm to stand out in memory. There was no urgency in the wind, no heaviness in the air. The sun hung high and proud, casting its rays on a motionless earth, illuminating fields, rooftops, sidewalks, and distant mountain ridges in a soft, steady light. Across towns and cities, everything seemed perfectly still. No drifting clouds. No shifting shadows. Just a sky so clear it seemed almost painted, brilliant, vast, and uninterrupted. Birdsong drifted lazily through open windows. Flags hung limp against their poles. In the distance, traffic moved with the sluggish ease of early afternoon. It was the type of weather that didn't demand your attention, the kind of sky that reassures you nothing unusual will happen today. Children played outside, stretching the final days of summer. Elderly couples sat quietly on porches, basking in the warmth. Farmers tilled soil. Workers took lunch breaks in open parks. Pilots flew commercial jets through the calm blue expanse without turbulence. The world, at that hour, felt balanced. And then, something changed. Something subtle at first, so subtle that most didn't even notice it. A faint vibration in the ground. A soft flicker in peripheral vision. A low, nearly inaudible pulse that echoed faintly like a drum beat behind the clouds, except there were no clouds. Just blue, stretching in all directions like an ocean of light. Then came a sound. A distant rumble. Deep. Ominous. It wasn't the metallic roar of machinery, or the whir of a passing jet. It was something far older, more primal. The kind of sound that makes the hairs on your arms rise before your brain even understands why. At first, people ignored it. They looked up, confused. Perhaps a storm on the horizon? But no. There was nothing to see. Not a puff of vapor in the entire sky. And yet that rumble, low, vibrating, alive, kept coming. A few began recording, holding phones to the sky as if the lenses could help make sense of the sound. Dogs began to bark. Birds took flight in frantic, irregular patterns. And then came the flash. It wasn't lightning as we know it. There was no forewarning, no streak racing across a darkened sky. It was instant, sudden and blinding, like a shutter snapping across the heavens. A single flash that painted shadows across walls and blinded drivers on open roads. And then, thunder. Real thunder. Not the distant grumble of an approaching storm, but a full-bodied, concussive roar that shook the ground and rattled windows. People stopped in their tracks. Coffee cups were dropped. Conversations halted mid-sentence. Construction workers paused, their tools humming in the silence that followed. In cities, high-rise residents stepped out onto balconies, shielding their eyes from the glare. In remote rural areas, farmers looked toward the sky with confusion painted across their sun-worn faces. The storm, if it could be called that, had arrived, without clouds, without warning, without precedent. Rain never fell. Winds never howled. But the sky lit up again. Another flash. Another crash of thunder that cracked like a whip through the atmosphere. And then another. The frequency began to rise. Not erratic, but rhythmic, almost like a slow heartbeat in the sky, steady, powerful, unrelenting. And still, the skies remained impossibly clear. Meteorologists were the first to question what was happening. Emergency scanners picked up bursts of chatter from confused air traffic controllers. Weather monitoring systems began pinging false alerts. Lightning strikes detected, yet no visual confirmation. Airports paused departures. Schools called parents. Power grids flickered in scattered regions. Social media exploded. Within minutes, hashtags began trending, phones lit up with alerts, and live streams poured in from different countries, all sharing one message: something very strange was happening above us. People who had never looked twice at the sky now stared into it with uncertainty. Something about the vast, perfect blue felt deceptive, as though it were hiding something just beneath the surface. The light no longer felt comforting. The silence between each thunderclap grew heavier. Even as the sky remained clear, Unease spread like a shadow over every street and suburb. It was not panic, not yet, but it was something close. The kind of collective awareness that humankind feels when nature acts in ways it never has before. In neighborhoods, clusters of neighbors gathered on sidewalks, watching, waiting. In offices, workers crowded near windows, pointing upward in disbelief. Weather enthusiasts pored over radar images, only to find that none of it made sense. Scientists sat in stunned silence. No forecasts had predicted this. No models accounted for it. No instruments could explain it. And all the while, the sky remained impossibly blue. Before we move on, we would like to encourage to consider subscribing and liking the video in order to support us in making more videos like this. As the world collectively turned its gaze skyward, meteorological agencies scrambled to process the sudden surge in thunder reports, incidents that defied the very models they'd come to rely on. In newsrooms and research labs alike, the question began to echo: how can thunder occur without clouds? The very notion seemed contradictory. But as weather stations began combing through their data, one potential clue began to emerge, not from above, but from the ground beneath our feet. Across multiple regions where this strange event was witnessed, one shared characteristic began to surface: an unusual spike in atmospheric pressure. On the surface, it seemed unremarkable. After all, pressure rises and falls every day. It's the invisible force we never think about. We feel its effects in the pop of our ears when flying or in the heaviness of air before a storm. But on this day, the barometers told a different story. Pressure was rising, fast. Not gradually as it typically does before a weather system rolls in, but sharply, almost unnaturally. Local weather enthusiasts, some with nothing more than backyard tools and a passion for patterns, noticed it first. Their digital readings began climbing beyond what was typical for that region and time of year. What was odd, however, was what wasn't happening. Normally, a spike like this would coincide with a visible change in the skies: cloud formation, wind shifts, maybe even the slow build of a thunderhead on the horizon. But here, the skies remained stubbornly blue. It was as if the atmosphere had been pressurized without the rest of nature catching up. This anomaly triggered an unusual theory among forecasters. What if the atmosphere itself had become unstable, not in the way we think of storms, with cold fronts slamming into warm ones, but in a quieter, more subtle way? Like a balloon being inflated past its safe point, the air may have reached a threshold where even the tiniest disturbance could trigger a release. In this case, not in the form of wind or rain, but sound. Thunder. The idea sounds strange because we're used to thunder being a consequence of lightning. A byproduct. Lightning strikes, the air rapidly expands, and thunder rolls across the sky. But in this instance, with lightning occurring without clouds, and thunder roaring without the traditional storm system, some scientists began to wonder: could changes in air pressure alone trigger acoustic phenomena? Could the sky itself be popping under the weight of its own imbalance? Imagine walking into a sealed room with perfect silence. Then imagine the pressure in that room climbing steadily, invisibly, until a sudden drop. A window shattering, a pipe bursting, a sound cracking through the stillness. That may be what happened on that eerily quiet day. A silent, invisible buildup that reached a breaking point. And what could cause such a pressure surge across multiple regions simultaneously? One possibility is solar interaction. Not dramatic solar flares or geomagnetic storms. Those make headlines and light up auroras. But subtler pulses of solar radiation that, while not dangerous, can influence atmospheric density. These gentle bursts often go unnoticed, rippling through our upper atmosphere and shifting the delicate balance between Earth's layers of air. Under normal conditions, the Earth absorbs and disperses this energy without issue. But on this day, something was different. The Sun, it turns out, had released a brief but potent stream of charged particles 2 days before the event. While it didn't make front-page news, satellites picked up on it. These particles, silent, invisible travelers from the Sun, can interact with our ionosphere, altering the way the atmosphere holds and distributes pressure. The result? A sudden, Widespread increase in upper-level density, pressing downward like an unseen hand. Not dangerous to humans, but possibly enough to create the perfect stage for a rare and sudden acoustic release. A thunderclap, with no visible storm. It's the kind of phenomenon that sits on the edge of current understanding. There are no names for it, no textbook category. And yet, the timing aligned. The solar stream, the pressure spike, the clear skies, all of it lined up too perfectly to dismiss. It was like a puzzle with too many matching pieces. For now, meteorologists are cautious. It's difficult to prove direct cause and effect when nature behaves in such unpredictable ways. But they continue to monitor the skies, comb through data logs, and rerun simulations. Because if it happens once, it can happen again. And next time, it might be louder, stronger, stranger. The skies were supposed to be predictable. But now, they're speaking in ways we've never heard before. While the initial reaction to the unexplained thunder was confusion, the mounting evidence surrounding atmospheric pressure changes, subtly influenced by solar particles, began to unfold like the early stages of a scientific mystery. But this was no ordinary puzzle. It was layered, elusive, and unlike anything atmospheric specialists were trained to anticipate. To understand the sheer complexity of what might have occurred, we have to consider just how delicate Earth's atmosphere really is. It's easy to think of the air around us as stable, almost static. We breathe it, we walk through it, and we rarely consider how dynamic and reactive it can be. But the truth is, our atmosphere is in constant motion, an ever-shifting blend of pressure zones, moisture levels, ionized particles, and invisible boundaries stacked like layers in a cosmic parfait. And when those layers shift, even slightly, unexpected things can happen. At the heart of this theory is the ionosphere, a high-altitude region of our atmosphere that extends roughly from 30 miles up to 600 miles above the surface. Most of us never think about it, but it's there, acting like a cosmic membrane that filters solar radiation and buffers Earth from the sun's more extreme emissions. During a solar particle event, even a minor one, the ionosphere doesn't just absorb the incoming energy, it becomes temporarily electrified, compressed, and reactive. Now, when this happens, there's often a cascade effect that begins to move downward through the atmospheric column. While we can't see it with the naked eye, instruments aboard satellites and high-altitude balloons record a ripple, a shift not unlike a drop of dye spreading through a glass of still water. It doesn't cause immediate destruction. There are no flashing warnings. But the pressure begins to subtly migrate. The molecules in the air begin to compact and rearrange in ways not typically captured by surface weather models. What we're looking at is a type of atmospheric resonance, a harmonizing of pressure zones that, under very specific conditions, can lead to bursts of sound. Not thunder in the traditional sense, but acoustic energy released suddenly, possibly even amplified by layers of dense air interacting with each other. Think of it like sound trapped between layers of glass. When pressure builds and is suddenly released, the noise can reverberate in unexpected ways. And from the ground, that might be perceived as thunder, even in the total absence of clouds. But the question remains, why here? Why now? Why in these precise areas, and not globally? The answer might lie in how unevenly the solar particles interact with Earth's magnetic field. Unlike light, which travels in a straight path, charged particles tend to follow magnetic lines, funneling into certain regions more than others, particularly near mid-latitudes and magnetic anomalies. One such anomaly exists over the South Atlantic, but there are lesser-known areas scattered across the globe, zones where the magnetic shielding is thinner, and solar particles are more likely to slip through. In those areas, the ionosphere may react more strongly to even small inputs of solar energy. When that energy trickles down, it doesn't just affect the upper atmosphere, it subtly alters the balance across the entire vertical column of air. Add in a temperature inversion, a layer where warm air sits on top of cooler air, and you have the perfect trap for energy. A sort of invisible dome that can hold and then abruptly release sound, like a speaker cone pressed to its limits. What's more chilling is that this kind of phenomenon may have occurred before, but without the instruments or awareness to capture it. Perhaps it was dismissed as distant thunder, or mistaken for sonic booms from passing aircraft. But this time, there were sensors. This time, people were watching. And this time, the sky was too clear, the sound too loud, and the data too unusual to ignore. The incident has prompted agencies to begin cross-referencing solar activity logs with unusual weather phenomena from recent years. Preliminary results are starting to reveal patterns, subtle correlations between minor solar events and unexplained atmospheric sounds. Not enough to claim a definitive link yet, but enough to raise eyebrows and prompt further study. There is also the question of whether climate change could be amplifying these effects. As global temperatures rise and atmospheric circulation patterns shift, the delicate equilibrium of our atmosphere may be becoming more volatile, more susceptible to outside influences. What was once a harmless influx of solar particles might now be interacting with an already stressed system, pushing it just past its tipping point. All of it paints a picture of a world more interconnected and more fragile than we ever imagined, where space weather influences terrestrial skies, where invisible changes in pressure might produce audible shocks, where the definition of a thunderstorm may need to be rewritten entirely. Whatever the true cause, one thing is certain: something shifted that day. And the sky, clear, blue, and deceptively calm, delivered a message we still don't fully understand. Still, as compelling as the solar ionospheric theory might seem, it's only one piece of a much larger puzzle. Because the mystery of thunder erupting from a sky devoid of clouds continues to challenge the assumptions we've long held about how weather behaves. And while the idea of upper atmospheric resonance has opened new doors in the conversation, other experts have begun turning their attention downward, to forces hidden not above us, but below. You see, in the days following the event, meteorologists weren't the only ones sifting through sensor data and playback footage. Seismologists, those who study the Earth's deep movements, quietly began examining their own logs, looking for any signs of tremors or vibrations that might have coincided with the event. And what some of them found was subtle, almost imperceptible, a brief, faint seismic signature. Nothing strong enough to shake buildings or even register consciously to those standing nearby. But it was there, like a whisper beneath the surface. This raised a new and equally perplexing possibility. Could the sound that people heard, described by witnesses as rolling thunder, have originated from underground? At first glance, it might sound implausible. After all, thunder is traditionally associated with the sky. But Earth has its own language of sound, its own deep, resonant frequencies that, when disturbed, can ripple through the ground and even transfer into the air. These phenomena are sometimes referred to as earthquakes without earthquakes, episodes where pressure builds within subterranean rock layers, only to release suddenly and with force, without the dramatic shaking typically associated with a seismic event. In some rare cases, this can create a phenomenon known as a booming ground sound, or more colloquially, skyquakes. These are explosive sounds that seem to come from above, but are actually triggered by subterranean shifts. They've been reported throughout history, strange, cannon-like rumbles in regions with no visible storms, sometimes so loud they cause windows to rattle or animals to flee. What's interesting is that these sounds don't always accompany major geological activity. Instead, they often occur in areas with underlying geological tension, where rock strata are slowly grinding against one another, storing up pressure over time. The release might be tiny in terms of seismic energy, but it can produce a loud acoustic event, particularly if the ground conditions allow for efficient transmission of sound. Loose soil, shallow bedrock, and certain temperature conditions can all conspire to funnel these noises upward, where they're mistaken for atmospheric phenomena. In the case of the recent Cloudless thunder event, some researchers began to speculate that what we heard wasn't thunder at all, but a subterranean release of pressure from deep within the Earth, possibly near a fault line or a shifting plate boundary. The sound may have simply echoed upward, traveling through layers of air that were unusually stable, giving it that rolling, lingering quality typically associated with a distant storm. Now here's where things get even stranger. This kind of sound transmission is more likely to occur under specific meteorological conditions. The atmosphere has to be calm, No wind, no precipitation, no turbulence. Essentially, the sky needs to be quiet enough to carry the sound, like a still lake carrying a skipping stone. On the day of the event, all those boxes were checked. The air was cool and settled. There were no low clouds or storms in nearby regions. It was, in other words, the perfect moment for an underground sound to rise unnoticed, until it exploded overhead like a phantom storm. What makes this idea particularly fascinating is how easily it can deceive the senses. Humans are hardwired to associate certain sounds with certain visuals. If we hear a crash or a boom, we instinctively look to the sky for lightning or clouds. But when none are present, our minds scramble to fill in the blanks. Could it be that this wasn't a breakdown in meteorological logic at all, but simply a misinterpretation of an underground event, filtered through the atmospheric conditions of that day? There's also the consideration of natural gas pockets and subterranean caverns. In certain regions, these cavities can collapse or shift slightly under pressure, sending shockwaves through the ground and up into the air. The result is a sudden, sharp sound, loud, resonant, and deeply unsettling. These types of events are rare, but not unheard of. And when they occur without visible surface damage, they can leave entire communities scratching their heads, wondering what on earth just happened. As scientists continue to dig deeper, literally and figuratively, into the circumstances surrounding this event, the idea of a subterranean cause has gained quiet traction. It's not the most visible theory, nor the flashiest, but it's rooted in the idea that Earth itself might be speaking, softly, and then all at once. So was it thunder from above, or a pulse from below masquerading as something else? The answers remain elusive. But as more data is analyzed, and more eyes turn to the ground beneath our feet, it's becoming increasingly clear that sometimes, to understand what's happening in the sky, we need to start looking underground. The notion that a sound, so unmistakably thunderous in tone, could rise not from the sky but from the ground beneath our feet is already compelling on its own. Yet what truly elevates this theory from a curious footnote to a subject of serious intrigue is how little we truly understand about the acoustic behavior of the Earth itself. For all our advancements in seismology, there remains a vast, largely unmapped world of micro-vibrations, subaudible frequencies, and geological murmurs that occur far beyond the reach of human hearing, but not beyond the reach of their effects. To grasp the full scope of this underground possibility, we must consider the nature of acoustic coupling, the process by which vibrations in one medium, like rock or soil, can transition into another, such as air. This isn't just a technical detail, it's the very gateway through which underground phenomena might breach the surface and manifest as audible sound. In highly specific conditions, the Earth can act as a sort of resonant chamber, a subterranean echo box that amplifies localized tremors or shifts into sounds loud enough to be mistaken for atmospheric events. There are documented instances where minor ground collapses, sinkhole activity, or sudden shifts in bedrock layers have triggered these peculiar audio events. These aren't dramatic earthquakes by any means, nothing that topples buildings or cracks roads. Instead, they're subtle but forceful energy releases. The kind that send a pressure wave upward, where it escapes into the open air with a percussive boom or a long, rolling roar. What's especially intriguing is that this kind of ground-to-air sound conversion often doesn't leave behind visible signs. No debris. No scars. Just a memory of the sound itself, and a lingering unease in the people who heard it. Geologically speaking, the areas most susceptible to this kind of event are often riddled with fractured bedrock, pockets of trapped gases, or shallow fault lines, regions where the Earth's crust is under constant micropressure. Over time, the stress accumulates. Layers of rock strain against each other until, with no obvious warning, a slippage occurs. Not enough to register on a national seismic scale, but enough to let off a sharp, violent burst of energy. That burst, depending on its depth and the conditions above, can take the form of a low-frequency rumble that travels straight upward and punches through the silence. Some researchers believe that seasonal changes may play a significant role in these kinds of events. As temperatures shift, the expansion and contraction of rock layers can amplify underground stress, especially in places where groundwater seeps into cracks and freezes or thaws with the seasons. The resulting changes in volume exert pressure on the surrounding rock, which can cause spontaneous microcollapses or sudden shifts. And when these collapses occur close enough to the surface, under a dry and stable atmosphere, the sound can erupt with shocking clarity. This could help explain why these thunder-like booms seem to occur in specific windows of time, and only under certain weather conditions, most often on crisp, quiet mornings or during periods of calm. There's even speculation among certain geophysicists that volcanic plumbing systems, the vast, interconnected tunnels of magma and gas beneath dormant or extinct volcanoes, might occasionally play a part in such phenomena. These subterranean networks can extend for miles beneath the surface, and while they may not be actively erupting, they can still exhibit internal movement. Gas buildups, pressure surges, and the slow, creeping shift of magma can all act like a percussionist tapping on the Earth's walls. And if one of these shifts releases a sudden pulse of energy, the sound might travel up through rock and soil, emerging as what people interpret as thunder. What makes this entire theory so captivating is how stealthy it all is. There's a certain uneasiness in the idea that the Earth could be shifting, breathing, booming, all while leaving no visible clue. It challenges the way we read our environment. We're trained to believe that big sounds come from big events, storms, explosions, crashes. But here, we're looking at the possibility that something massive could be speaking through subtlety. A deep, wordless message that rumbles through the bones of the world and erupts into the air with no storm to show for it. In fact, this kind of event may not be a one-off at all. Some believe we've simply been misattributing these sounds for years. That what we call mystery booms, skyquakes, or phantom thunder are all part of a broader geological conversation that we've only just begun to notice. Maybe the Earth has been doing this all along. We just haven't been listening closely enough. It's a chilling thought, this idea that beneath the comforting illusion of stillness, there's a hidden world of sound and movement. That while we go about our daily lives under open blue skies, something far older, far deeper is shifting slowly beneath our feet, and every once in a while, it speaks. While the notion of underground forces giving rise to thunder-like booms offers a grounded, even tangible explanation, not all observers are convinced that the source lies beneath our feet. In fact, there is a growing corner of speculation that suggests we may need to look upward once more, but not at the clouds. Instead, this theory asks us to turn our attention to the upper layers of the atmosphere, and beyond. Because there's something else that can cause noise on a scale so vast, so seemingly sudden, it doesn't require a single cloud to make its presence known. This time, the potential cause doesn't come from the ground, or even the sky as we understand it. It may originate from above the atmosphere altogether. Imagine this: you're standing outside on a bright, clear day. The sun is steady. The breeze is still. There's no static in the air, no distant rumble building in the distance, no warning. And then, out of nowhere, the sky cracks open, not with rain or lightning, but with a single, deep boom that rolls through your chest like the world just shifted. But there's nothing. No flash. No windswept storm clouds gathering overhead. Just that sound, isolated, raw, and completely out of place. The silence that follows it feels even more unnatural, as though something came and went. Some theorists believe this could be the byproduct of what are called high atmospheric energy discharges, events that occur so far above the weather system that they defy traditional classification. These aren't lightning bolts, not in the way we typically understand them. They are more like bursting bubbles of plasma, invisible to the naked eye from the ground, but carrying enormous energy. These pulses could, in theory, be triggered by anything from shifts in the ionosphere to interactions with solar radiation. And when they occur, they don't follow the familiar path of thunderclouds. Instead, they release a compression wave so vast and so sudden that the sound travels down in a singular boom, completely disconnected from any visible sign of atmospheric disturbance. These kinds of upper atmospheric events are hard to study, nearly impossible to predict. They happen at altitudes where our planes don't fly, where our weather balloons barely reach, and where our satellites can only detect the faintest traces of change. Yet we know this region is full of surprises. The upper atmosphere is dynamic, constantly shifting in ways we're still learning to map. Charged particles, electromagnetic fields, microbursts of energy. This invisible ocean of air and radiation could be holding secrets we've yet to name. There have even been instances, though rarely confirmed, where pilots flying at extremely high altitudes have reported strange pressure jolts or unexplained booms, even while passing through clear skies. These moments are often brushed off as atmospheric anomalies. But what if they're actually the audible footprints of something bigger? Something that doesn't follow the rules of terrestrial weather? These booming sounds might be the final echo of a momentary disturbance that appeared thousands of feet above us, and disappeared just as quickly, leaving no evidence except for sound. What gives this idea an eerie plausibility is how abrupt and localized the booms are. Thunder from a traditional storm rolls in gradually, you can feel it building. But with these skycrack events, people describe something instantaneous, like a detonation, without the destruction. A phenomenon that lasts only a few seconds yet feels as though it punctured the world itself. Theories like this edge into the unknown, brushing against the boundaries of meteorology, space weather, and even geophysics, but they're difficult to dismiss outright. Not because we have proof, but because we don't have enough proof to rule them out. It's important to remember that our atmosphere isn't just a passive blanket of gases, it's a living, breathing, electric system. And much of it behaves in ways that still defy prediction. Scientists have only just begun to study upper atmospheric phenomena like sprites, jets, and elves, brilliant flashes of red or blue light that erupt above thunderclouds during lightning storms. For decades, these were dismissed as myth, strange tales from pilots and remote observers. But now, with modern cameras and satellite systems, we know they're real. They were happening all along. We just didn't have the tools, or the imagination, to catch them. So what else might be happening up there that we simply haven't seen yet? If the skies can light up with electrical events we didn't even know existed until the last few decades, then maybe they can also sound off in ways we haven't learned to detect. A new kind of sonic expression. A kind of skyquake, not born from the ground, but from something even more elusive, like a ripple in the upper layers of the Earth's magnetic envelope. As speculative as this theory may seem, it carries a strange logic. A clear day doesn't mean a quiet one. The absence of clouds doesn't guarantee stillness. And sound doesn't always come from the things we can see. Sometimes, the atmosphere itself may speak, not with lightning, not with wind, but with a voice that rolls down from the edge of space, booming across a cloudless sky, leaving us stunned, confused, and deeply aware of how much we still don't know. If we entertain the possibility that the upper atmosphere might be responsible for these mysterious booms, these thunderous ruptures in an otherwise flawless sky, then we must also consider just how little we truly understand about what's unfolding above us at any given moment. It's easy to imagine the atmosphere as something static, divided neatly into layers we've named and charted: the troposphere, the stratosphere, the mesosphere, and so on. But in reality, these boundaries are not rigid. They shift and fluctuate, expanding and contracting depending on time of day, solar activity, and even subtle changes in global weather systems. Above the weather, past the highest drifting clouds and well beyond the altitude of most aircraft, lies a region teeming with invisible forces. These aren't the winds and rains we can see, but instead fields of charged particles, electromagnetic pulses, and waves of energy cascading from interactions between Earth and the Sun. And here, in this fragile no-man's land between our world and space, strange things can, and do, happen. It's not unreasonable to imagine that something could shift up there, temporarily discharging or compressing energy in a way that causes a sharp acoustic wave to travel downward, shattering the illusion of calm. We often picture space weather as something distant, solar flares hitting satellites, or auroras painting the polar skies. But the truth is that these celestial events don't just impact what's out there. They touch us here too. Solar storms can influence Earth's magnetic field, disrupt communications, and even cause surges in power grids. Yet their effect on our atmosphere, particularly the upper atmosphere, is still a realm of open questions. When radiation from the sun interacts with the ionosphere, could it be generating more than just electromagnetic noise? Could it occasionally produce a sudden, focused burst of energy that manifests not visually, but audibly? Now think about the concept of resonance, the way certain frequencies can cause structures to vibrate, or even shatter glass. What if similar principles apply to the thin, stretched layers of the upper atmosphere? If an electromagnetic pulse or a surge of solar energy were to hit just right, in just the right conditions, could it set off a resonant wave through the upper air, amplifying itself as it moved downward until it finally became audible? A kind of skyborne shockwave, unaccompanied by lightning, clouds, or any of the hallmarks of a conventional thunderstorm? It sounds like science fiction. But consider this: the upper atmosphere isn't empty. It's filled with tiny particles, charged atoms, and gases at extremely low pressures, conditions that, under the right influence, could behave unpredictably. The transition from space to Earth isn't a clean break. It's a gradient of energy and interaction, and that middle zone may be capable of producing phenomena we have no current model for. The boom heard from below might be the final echo of a massive, invisible collision above, between solar energy and the Earth's atmospheric shield. And perhaps most fascinating of all is the localized nature of these events. Witnesses often report that only a small area was affected by the sound, that a friend standing a few miles away heard nothing, while they felt it in their chest. This is not how thunder behaves. Thunder rolls and echoes. It spreads out over wide distances. But this is precise. Focused. It's as if a targeted pulse was sent directly down from some high-altitude event, like a sonic needle threading its way from the edge of space straight to the ground. Then there's the question of detection. Our instruments, as sophisticated as they are, have blind spots, especially when it comes to brief, non-visual, high-altitude disturbances. Satellites, while powerful, are optimized for long-term tracking, not spontaneous noise. Ground-based radars are tuned to specific altitudes and weather types. Even atmospheric microphones used to detect nuclear tests or volcanic eruptions might miss something that occurs in a narrow frequency band or dissipates too quickly. That means it's entirely possible for a high atmospheric boom to go undetected by every formal system we have, while still being experienced as a real, physical event by the people below. In that sense, we may be hearing the unseen turbulence of our own sky, a murmur from a layer of air too high to observe, too fleeting to record, but still capable of shaking us to our core. We live under an atmosphere that is constantly in motion, stirred by solar winds, electrical storms above the clouds, and perhaps other forces we haven't even begun to classify. Each boom, each moment of thunder without a storm, could be a signal, not from a distant planet, but from the ever-changing, dynamic ceiling of our own world. The sky, it seems, may not be as silent as it appears. And perhaps, every once in a while, it speaks, not in light, or in storm, but in sound. What does it mean when the sky no longer follows the rules we thought we understood? When thunder rolls from a blue sky, untouched by clouds, and no one can say why, what does that tell us, not just about the atmosphere, but about ourselves? Because events like this, as rare and fleeting as they may seem, have a way of challenging something deeply embedded in our collective psyche, our belief that we've already figured most things out. That the world, and by extension the universe, follows a script we've more or less decoded. We track hurricanes before they land. We predict eclipses centuries in advance. We send spacecraft beyond the pull of Earth's gravity, armed with precise coordinates. And yet the thunderclap from a cloudless sky brings all that certainty into question, not violently, not destructively, but subtly, like a whisper from the unknown. In that moment, when the sound tears through the calm and all eyes turn upward, we are reminded of something ancient and often forgotten, that we are still at the mercy of forces we do not fully understand. Despite our technological towers and digital fortresses, despite our satellites and storm tracking systems, there are things that remain just beyond our reach. It is a humbling realization. One that doesn't bring fear, necessarily, but awe, wonder. A quiet pause in the mind, as if the world is gently nudging us to look again, to listen closer, to not let our knowledge become our blindness. For centuries, the sky has been a canvas for human meaning. From ancient civilizations who saw gods in the clouds to philosophers who searched the heavens for patterns and purpose, we've always looked up for answers. And maybe, just maybe, this sound, the unprovoked roar from a placid sky, is not just a scientific anomaly, but a reminder that our story is still unfolding. That nature still holds chapters we haven't read. And more importantly, that we are still students of this earth, not its masters. There is something poetic about the idea that nature chooses silence most of the time, chooses predictability, repetition, order, but every now and then, it breaks its own rhythm. It makes a noise where there should be none. A single strike of unexplainable sound that slices through our routines, our expectations. It's as if the planet itself is reminding us that certainty is a luxury, not a guarantee. And this has broader implications, not just for scientists or sky watchers, but for humanity as a whole. Because if we can be surprised by the sky, something so vast and familiar and seemingly understood, what else might we be overlooking? What other phenomena are occurring right now, just out of range of our instruments or our assumptions? Perhaps this is a call to curiosity, to remain open, to question even what seems settled. Maybe the most dangerous thing isn't the unknown itself, but the comfort of thinking there's nothing left to discover. These thunderless storms, these voiceless voices in the air, challenge us in the most profound way. They don't threaten our lives but our worldview. They invite us to wonder again. And in a world where so much has become automated, optimized, and explained, that invitation is priceless. In the end, this could be more than a strange meteorological event. It could be a moment of reconnection between us and the world we walk on and breathe in every day. A soft rupture in the veil of everyday understanding. A cosmic nudge. And perhaps, just perhaps, that is its greatest message. As we bring this exploration to a close, we can't help but reflect on the extraordinary mystery that unfolded right before our eyes. A thunderstorm that formed from a clear, cloudless sky. On the surface, it seems simple, almost mundane, but beneath that simplicity lies a whirlwind of complexity, wonder, and uncertainty. What we thought we knew about the weather, the sky, and the forces that shape our planet has been called into question, and in the process, we've been reminded of just how little we truly understand. From the very first rumble of thunder to the lingering questions that followed, this seemingly simple event opened the door to a world of unknowns. Could it be that the laws we've relied on for centuries are not as rigid as we once thought? Could there be forces at play that are so subtle, so elusive, that they slip through the cracks of our understanding? Or perhaps there's something deeper at work here, a challenge, not just to the way we perceive the sky, but to the way we perceive our place in the universe. The first theory we explored suggested that these kinds of storms could be the result of complex atmospheric conditions that we're only beginning to understand. The idea of atmospheric gravity waves, ripples in the air that travel with such force and speed that they could trigger a sudden, unanticipated thunderstorm, felt like the most plausible explanation. These invisible waves, generated by shifts in temperature or air pressure, could move through the atmosphere undetected by conventional weather systems until they suddenly reach a tipping point. At that moment, the calm sky erupts in thunder, a stark reminder that the atmosphere is never as still as it appears. It's a dance of forces, invisible to the naked eye, and we, too often, forget just how much we don't see. But we didn't stop there. We dug deeper. We turned our gaze to the effect of urbanization on the weather, particularly the phenomenon of urban heat islands. The idea that a seemingly random thunderstorm could actually be the result of the growing warmth of urban environments is an intriguing one. Cities, with their concrete and steel, absorb heat in ways that disrupt natural airflow, making them hotspots for turbulence in the atmosphere. This theory paints a picture of a world where our cities are no longer passive landscapes, but active participants in the processes of nature, altering the very skies above us. What's more, it forces us to consider the long-term effects of urbanization on weather patterns, effects that we may not even be able to predict yet. As we ventured further into more speculative territory, we began to entertain the idea of anomalous forces at work beyond the reach of conventional science. Could it be that what we experienced was some sort of electromagnetic anomaly, a surge in energy so powerful that it created an unforeseen chain reaction, triggering a thunderstorm without the usual cloud formation? Or maybe the event was caused by an unseen atmospheric imbalance, a disruption so subtle that it eluded even the most advanced instruments, yet powerful enough to make the air tremble. This line of thinking invited us to explore the boundaries of what we think we know, to embrace the possibility that nature might be far stranger than we can even imagine. Then, we shifted focus once more, drawing our attention to the broader implications of such an event. What does it mean when the very rules of nature seem to bend? This thunderstorm, appearing out of nowhere, became more than just a meteorological anomaly. It became a profound metaphor for the mysteries of the universe, those forces and phenomena that still elude our grasp. We looked at how, despite all our technological advances, we are still in the midst of an unfolding story, a story that asks us to remain humble and curious, always seeking to learn more, to look deeper, to ask more questions. Nature, in all its vast complexity, continues to remind us that there is much we do not know, and sometimes the most powerful lesson is in that very uncertainty. The event was also a reminder that we, as humans, are part of something much greater than ourselves. The thunderstorm that broke the sky was not a sign of chaos, but a symbol of interconnection, the idea that everything in this world is linked, from the smallest molecule in the air to the vast, uncharted forces shaping the atmosphere. It made us consider the way our existence is intertwined with the natural world. We cannot control it all, no matter how advanced our science becomes. Sometimes, it's not about controlling the storm, it's about listening to it, understanding it, and learning from it. Ultimately, what does this thunderstorm in a cloudless sky teach us? It teaches us that the world we live in is not static, it's dynamic, ever-changing, and full of surprises. The weather, like life itself, is full of twists and turns, unpredictability, and wonder. We have our theories, our explanations, our data, but nature continues to push us to dig deeper, to stretch the boundaries of our knowledge, and to never stop questioning. In a world that often feels defined by certainty, moments like these remind us of the beauty and the power of mystery. As we step away from this strange event and back into the rhythms of our daily lives, let's remember the thunder that startled us from a clear sky, and let it serve as a reminder. There is so much more waiting to be discovered, more to learn, and more to wonder about than we can ever imagine. Whether it's a shift in the atmosphere or a shift in our understanding, the world is full of awe, and it's in the unknown that we find the greatest opportunities for growth and discovery. Let this thunderstorm be more than just a headline. Let it be an invitation to ask more questions, to explore the uncharted corners of our world, and to embrace the mystery of the universe that, like the sky above, is vast, open, and filled with possibility. If you've found this deep dive into the mysterious thunderstorm as fascinating as we have, don't forget to like this video and subscribe to our channel. There's so much more to explore, and we wouldn't want you to miss out on the next journey into the unknown. Hit the bell icon so you'll always be the first to know when we uncover the next mystery. Stay curious, and we'll see you in the next video.